Introduction. Science is full of mysteries, questions that twist logic, defy intuition, and make even the greatest minds pause in silence. Tonight, we'll explore the most mind-bending paradoxes ever discovered. Ideas so strange they blur the line between reality and illusion. From time travel to black holes, from quantum puzzles to the nature of identity, each story will pull you deeper into the beautiful contradictions of our universe. So, lie back, relax, and let's begin our quiet journey through the greatest paradoxes in science. The twin paradox. Imagine two brothers, born at the same moment, identical in every possible way. Their lives begin together, yet destiny soon draws a line through time itself. One brother remains on Earth, living a quiet and ordinary life. The other becomes an astronaut, traveling through the cosmos at a speed close to that of light. This is where one of the most mind-bending paradoxes in physics begins, the twin paradox. According to Einstein's theory of special relativity, time is not a universal constant. It bends and stretches depending on how fast one moves through space. The faster an object travels, the slower time passes for it relative to those who stay still. To most people, this sounds like an illusion, a trick of perception. But relativity is not a metaphor. It is a physical truth, one that has been confirmed again and again in experiment and observation. So the story unfolds. The traveling twin boards his spacecraft and leaves Earth behind. As he accelerates to nearly the speed of light, time begins to slow for him. His heart beats more slowly, his thoughts flow more slowly, and even the ticking of his onboard clock drifts behind. Meanwhile, his brother on Earth continues to age at a normal rate, counting the years as they pass. For the twin in space, the journey might feel like only a few short years, while for the twin on Earth, decades could have slipped away. At first glance, it seems both twins should see the other as aging more slowly. After all, from each twin's perspective, the other is the one moving. That is the essence of the paradox. If motion is relative, how can both be right? The answer lies in acceleration. When the traveling twin turns around to return home, he experiences a change in velocity, a moment when his frame of reference is no longer equal to that of his brother. This break in symmetry resolves the paradox. The twin who experienced acceleration and deceleration is not the same as the one who remained at rest. And because of this, when they reunite, the traveling twin will indeed be younger. This is not a thought experiment detached from reality. In the real world, scientists have tested the principle with extraordinary precision. Atomic clocks flown on airplanes or placed on satellites orbiting Earth have been shown to tick more slowly compared to identical clocks left on the ground. The difference is small nanoseconds, perhaps, but it is measurable. Our GPS systems even rely on correcting for this relativistic time dilation, ensuring that satellites high above the planet stay synchronized with clocks on Earth. Without Einstein's equations, navigation itself would drift into error. The beauty of the twin paradox lies in its quiet revelation. Time is not absolute. It is woven together with space into a single, flexible fabric that responds to motion and gravity. The universe does not flow uniformly like a great clock. Rather, it adapts to the paths of those who move within it. What feels like seconds to one person may feel like minutes or hours to another, depending on their velocity and their position in the cosmic landscape. The emotional undertone of this paradox is just as striking as the physics. Imagine the moment of reunion. The brother who left Earth returns home to find that his twin has grown old. The trees he once knew have matured, cities have changed, and perhaps centuries have passed. For him, only a few years have slipped by. The symmetry of their shared birth is broken by the great ocean of time itself. It is a quiet and haunting image, one that connects the deepest equations of physics to the human experience of separation, loss, and wonder. At its core, the twin paradox is not truly a contradiction. It is a mirror that reflects our assumptions about time and existence. It teaches us that the passage of time depends on where we stand, how we move, and what forces shape our journey through the universe. In Einstein's vision, space and time are not static backdrops, but living dimensions, continuously sculpted by motion and gravity. And so, the story of the two brothers becomes more than a scientific curiosity. It becomes a gentle meditation on the nature of reality. Every heartbeat, every second, every breath we take is part of a cosmic rhythm that stretches across the stars. Time does not simply pass. It flows differently for each of us, depending on the path we follow. The twin paradox reminds us that our universe is far stranger than our senses allow us to see. It is not built on rigid walls of logic, but on the soft and flexible fabric of relativity, a fabric where two brothers can share the same birth, yet live in different centuries of time. The quantum Zeno paradox. In the strange world of quantum mechanics, motion and stillness are not what they seem. The quantum Zeno paradox begins with a simple but unsettling idea. The act of observation can prevent change itself. A system that is constantly measured, watched, or observed will appear to freeze in place, unable to evolve. It is as if time itself pauses under the gaze of awareness. The name comes from the ancient Greek philosopher Zeno, who proposed paradoxes about motion long before quantum physics existed. He argued that an arrow in flight, when observed at any given instant, is motionless. If every instant is still, how can motion ever occur? 2,000 years later, physicists found that something eerily similar happens in the microscopic world, not as philosophy, but as measurable reality. In the quantum realm, particles exist in fragile states of probability. An atom may be excited, waiting to release energy, or it may remain in its ground state. These states are not definite until an observation is made. Between measurements, the particle evolves naturally according to the laws of quantum mechanics. But when it is observed, when its state is measured, that delicate evolution collapses into a single outcome. If you continue to observe it again and again, almost continuously, the transition never happens. The system becomes locked, frozen by attention. This is the quantum Zeno effect. Continuous observation inhibits change. It was first described theoretically in the 1970s by George Sudarshan and Badyainath Mishra, who noticed that quantum systems behave like Zeno's arrow. The more frequently you check their state, the less they seem to change. Decades later, physicists proved it in the laboratory, using trapped ions and atoms cooled to near absolute zero. By measuring them repeatedly, researchers found that they could slow down or even halt their natural decay. Observation had become a kind of control. At first, this seems like a contradiction. How can looking at something stop it from evolving? But in quantum mechanics, observation is not passive. It is an interaction, a disturbance, a participation in the system's evolution. Measuring a quantum state is like touching a ripple on water. The act itself alters what is being observed. The wave of probability collapses into a fixed point, and in doing so, resets the system's evolution each time. In a broader sense, this paradox reveals the intimate connection between knowledge and reality. In the macroscopic world, we assume that things exist independently of whether we see them. But in the quantum world, measurement is part of existence. A particle has no definite position until we measure it. Its energy, spin, and even its lifetime depend on how we choose to observe it. The quantum Zeno paradox exposes this deep truth, that observation and being are intertwined. The effect is not just a theoretical curiosity. It has real implications for quantum technology. In quantum computing, for example, fragile bits of quantum information, qubits, can easily lose coherence, their delicate states collapsing through unwanted interactions. But through controlled observation, scientists have learned to stabilize them, preventing decay much like the Zeno effect freezes atomic transitions. By carefully managing when and how a system is watched, they can extend its lifespan and maintain quantum order against the natural pull of chaos. There is a quiet irony in this phenomenon. The more attention we give to a system, the less it changes. Observation becomes preservation. In a way, it mirrors aspects of human perception and consciousness. Focus holds a moment still. Awareness stops the flow. In the quantum world, this is not metaphor but reality. A watched atom refuses to move, just as Zeno's arrow refuses to fly. When the observation ends, motion returns. The atom resumes its natural evolution. The wave function spreads again, and the universe continues to unfold as it always does. Restless, uncertain, and alive. The quantum Zeno paradox does not break the laws of physics. It deepens them. It shows that at the smallest scales of existence, reality is not merely observed. It is shaped by the act of observation itself. And so, within this paradox lies a quiet reflection about the nature of time and awareness. Every act of measurement, every moment of perception, leaves a trace upon the universe. When we look, we change what we see. When we stop looking, the universe moves on. The quantum Zeno paradox reminds us that motion, change, and even time depend on the rhythm of observation. What we call stillness may only be the illusion created by constant attention, the universe holding its breath under the steady gaze of the observer. The grandfather paradox. Among the many puzzles of time and causality, few are as famous or unsettling as the grandfather paradox. It begins with a simple act of imagination, a journey backward through time. In this thought experiment, a person travels into the past and encounters their own grandfather before the traveler's parent has been born. Through some interference or accident, the traveler prevents the grandfather from having children. The paradox emerges at that very moment. If the grandfather never becomes a parent, the traveler could never be born, and therefore could never have traveled back in time to alter that past. This loop of contradiction strikes at the very heart of logic and causation. Cause and effect, the sequence upon which reality itself depends, begins to collapse. The grandfather paradox is not just a philosophical riddle. It is a test of whether time travel, as imagined in physics, could ever be consistent with the laws of the universe. In the classical sense, time is linear. One moment follows another in an unbroken chain. The past leads to the present, and the present shapes the future. But Einstein's theory of relativity opened a door that once seemed locked forever. It showed that time is not absolute but relative. It bends under gravity and can even form loops in certain solutions to his equations. The possibility of closed time-like curves suggested that, at least in theory, paths might exist that lead back to earlier points in time. Yet these paths come with consequences that challenge everything we understand about logic. The grandfather paradox represents the collision between mathematical possibility and philosophical impossibility. It demonstrates that even if the laws of physics allow travel through time, our understanding of causality may not survive the journey. A universe in which events can rewrite their own history seems unstable, perhaps even incoherent. To preserve order, something must intervene, a principle or mechanism that keeps paradoxes from unfolding. One such idea is known as the Novikov self-consistency principle. It proposes that the universe forbids paradoxes by design. According to this principle, any action taken by a time traveler was always part of history, even if it appears to change it. The traveler's interference cannot alter the timeline because the timeline already includes the interference. In this view, the traveler who visits the past might try to prevent their grandfather's survival, but circumstances will always conspire to stop them. Reality bends, but never breaks. Another interpretation, drawn from quantum theory, imagines the creation of branching timelines. When a traveler alters the past, the universe splits, one branch where the event occurred as before, and another where the change takes effect. In one world, the grandfather lives. In the other, he does not. The traveler continues to exist, but now within a different version of reality. This approach removes the contradiction, but at the cost of multiplying worlds without end. Whether or not such branching universes exist is unknown. The paradox remains unresolved, resting in the space between physics and philosophy. Yet it serves an important role. It exposes the fragility of our intuition about time. We tend to imagine time as a river that flows in one direction, but the equations of relativity do not enforce such limits. They allow motion both forward and backward, symmetry in both directions. The grandfather paradox reveals what happens when that symmetry collides with the logic of human experience. The paradox has become a cornerstone in the study of time travel and theoretical physics. It is not merely a curiosity of imagination, but a conceptual test of consistency in any model of spacetime. Scientists who explore wormholes, cosmic strings, or other exotic structures must consider it carefully. If a theory allows travel to the past, it must also account for the preservation of causality, or find a reason why paradoxes cannot physically occur. In the quiet depth of this paradox lies a profound lesson. Time may not be what it seems, yet it resists contradiction. The universe may allow extreme distortions of space and time, but it protects coherence, preserving the continuity of cause and effect. The grandfather paradox is therefore not a failure of reason, but a mirror reflecting the boundaries of what is possible. It is a story about limits, the limit of logic, the limit of human understanding, and the limit of how far reality can bend before it fractures. It reminds us that the past is not simply a place we can visit, but an integral thread in the fabric of existence. To pull on that thread too strongly would unravel the tapestry itself. In the end, the grandfather paradox remains one of the most haunting questions in modern physics. It stands at the crossroads of science and philosophy, where time, identity, and existence meet in a single impossible loop. And though it may never be resolved, it continues to draw our minds toward the quiet mystery of time, a dimension that allows all things to happen, but perhaps not to happen twice. The Fermi Paradox. In the summer of 1950, at the Los Alamos National Laboratory, a group of physicists gathered for lunch. Among them was Enrico Fermi, one of the great scientific minds of the 20th century. As the conversation drifted toward the topic of extraterrestrial life, Fermi paused and asked a simple, quiet question: "Where's everybody?" It was a moment of clarity that would echo through decades of scientific thought. The question captured a contradiction so deep that it became one of the most enduring puzzles in modern science: the Fermi Paradox. At its core, the paradox is a comparison between probability and observation. The universe is vast beyond comprehension. There are hundreds of billions of galaxies, each containing hundreds of billions of stars, many surrounded by planets. Statistically, even if a tiny fraction of those planets developed conditions similar to Earth, there should be countless worlds where life could emerge. And if intelligent civilizations had arisen long before humanity, their presence should be visible by now, through signals, probes, or cosmic engineering on a galactic scale. Yet, the night sky remains silent. Our telescopes scan the heavens. Our antennas listen for whispers of communication, but no sign has come. There are no detectable spacecraft, no interstellar beacons, no evidence of alien technology. The contradiction between the high probability of extraterrestrial civilizations and the complete absence of contact or observation is what defines the Fermi paradox. Over the decades, scientists have proposed many possible explanations. Some suggest that intelligent life is extraordinarily rare, that while simple organisms may arise easily, the leap to consciousness and technology is almost impossible. Others believe civilizations may be common, but short-lived. Advanced societies could destroy themselves through conflict, exhaustion of resources, or uncontrollable technology before ever reaching the stars. Another idea is that the universe may be filled with life, but separated by vast distances that make communication impossible. Even traveling at a fraction of the speed of light, the journey between stars could take millennia. Perhaps civilizations exist, but are simply too far apart to ever meet. A darker possibility imagines a galaxy where silence is intentional. According to the dark forest hypothesis, every civilization hides, knowing that revealing itself could invite destruction from others. In such a universe, survival demands secrecy, and the absence of contact is not emptiness, but caution. Some physicists and astronomers turn the paradox inward. They argue that perhaps we are not listening correctly, that alien communication might not come in radio waves or visible light, but in forms of energy or dimensions we cannot yet detect. What we interpret as silence could be our own technological blindness, a gap between how we search and how others might exist. Others suggest that the Earth and its inhabitants are part of a kind of cosmic isolation. Maybe advanced civilizations avoid contact with younger ones, allowing them to evolve undisturbed, a concept known as the zoo hypothesis. In this scenario, humanity is not ignored, but observed, like a species in a vast cosmic preserve, unaware of the watchers beyond the stars. Despite the many theories, no answer satisfies completely. The Fermi paradox remains suspended between possibility and mystery. Its strength lies in how it challenges our assumptions, not only about life elsewhere, but about our place in the universe. For billions of years, the cosmos has unfolded without witnesses. If intelligence is rare, then we may be one of the few sparks of awareness to ever arise. If it is common, then we are living in the quiet interval before discovery. The paradox touches something deeper than science. It evokes the loneliness of existence, the smallness of our world against the vast, indifferent night. It reminds us that every radio transmission sent into space is both a scientific experiment and a gesture of hope, a faint signal crossing the darkness, searching for an echo that may never come. And yet, the silence may itself hold meaning. In that silence lies the measure of human curiosity, the endless drive to understand. The Fermi Paradox is not simply a question about others. It is a mirror reflecting our own need to reach beyond ourselves, to know that we are not alone. In the quiet rhythm of the stars, the paradox continues to live. It humbles us with scale, challenges us with reason, and invites us to listen. Whether the universe is teeming with life or hauntingly empty, the mystery endures. A gentle reminder that our greatest discoveries often begin not with answers, but with silence. The Bootstrap Paradox. Imagine a scientist who travels back in time, carrying with them the manuscript of a groundbreaking invention. They meet a young inventor in the past and give them the manuscript, explaining that it is their own future work. The young inventor studies it, replicates the design, and eventually becomes famous for creating it. Years later, after the invention changes the world, the inventor grows old, builds a time machine, and travels back to the moment they once met their younger self, to hand over the same manuscript. Here lies the paradox. Who actually created the invention? If the manuscript was given to the inventor by their older self, and that manuscript was originally obtained from their younger self, the information seems to exist in a closed loop with no clear origin. It has no point of creation, it simply exists. This is the essence of the Bootstrap Paradox, one of the most mind-bending puzzles in time travel and physics. The term bootstrap comes from the phrase, pulling oneself up by one's bootstraps, describing something that causes or creates itself without any external input. It is a logical loop where cause and effect blur until they are indistinguishable. In theoretical physics and philosophy of time, this paradox questions the very foundation of causality, the idea that every effect must have a cause. If an object, idea, or person travels through time in a loop and becomes its own origin, the causal chain breaks. The event seems to sustain itself eternally, existing independently of any beginning. A famous fictional example is found in Doctor Who. A musician receives a song from their future self, records it, and later becomes known as the song's creator, only to one day go back in time and give it to their younger self again. The song has no original author. It simply exists in the timeline, looping forever. Scientists and philosophers have explored whether such paradoxes could exist in a universe governed by the laws of physics. Some theories, such as those involving closed time-like curves in Einstein's general relativity, suggest that under certain extreme conditions, like near a rotating black hole, time could theoretically loop back on itself. In such a universe, the Bootstrap Paradox could occur without violating the equations of physics. But whether reality allows this is another question entirely. Quantum mechanics adds another layer to the puzzle. According to the many worlds interpretation, time travel might create alternate timelines rather than loops. In this view, when someone travels back in time and influences the past, they branch into a new timeline where events unfold differently. Thus, the paradox dissolves, because the version of reality that receives the future object is not the same one that created it. The original timeline continues untouched. But even this explanation leaves something hauntingly unresolved. The Bootstrap Paradox invites us to consider that perhaps our universe is not a neat chain of cause and effect, but rather a vast, interconnected web of events, where time is not strictly linear, but circular, self-referential, and deeply mysterious. When we think about the paradox deeply, it feels less like a contradiction and more like a whisper from a higher logic, a suggestion that reality itself might be built on patterns that fold back upon themselves. Like a story with no first page, yet complete in its meaning. The Bootstrap Paradox reminds us that the boundaries of science and philosophy often meet where our understanding of time begins to unravel. And perhaps, Somewhere in that infinite loop, the universe is quietly sustaining itself without ever needing a beginning. The black hole information paradox. In the deepest reaches of space, there are places where gravity becomes so powerful that nothing, not even light, can escape. These are black holes, the ultimate endpoints of massive stars. They are regions where the known laws of physics collapse into a singular point of infinite density, surrounded by a mysterious boundary known as the event horizon. What falls beyond this horizon is said to be lost forever. But here begins one of the most profound mysteries in modern physics: the black hole information paradox. In the 1970s, Stephen Hawking made a groundbreaking discovery. He showed that black holes are not entirely black. Due to quantum effects near the event horizon, they emit faint radiation, now known as Hawking radiation. Over immense timescales, this radiation causes the black hole to slowly lose mass and eventually evaporate completely. At first, this seemed like a fascinating insight into the nature of quantum gravity. But then came a devastating realization. If a black hole evaporates completely, what happens to the information about everything that ever fell inside? According to quantum mechanics, information cannot be destroyed. Every particle, every bit of energy, carries quantum information, details about its state, spin, charge, and position. The universe, in principle, must preserve all of it. This is called unitarity, the rule that the evolution of quantum systems is perfectly reversible. But general relativity, the theory that describes black holes, says something different. It says that once something crosses the event horizon, it is cut off from the rest of the universe forever. When the black hole eventually disappears, the information inside seems to vanish with it. This creates a contradiction between the two pillars of modern physics. If information truly disappears, quantum mechanics is wrong. If information survives, our understanding of spacetime itself must be incomplete. Physicists have spent decades trying to reconcile this paradox. Some suggest that the information is somehow encoded in the Hawking radiation itself, subtly imprinted in the random quantum noise that escapes. Others propose that the information remains on the surface of the event horizon, stored like a hologram on a cosmic boundary. This idea led to the holographic principle, a radical notion that the entire universe might be a kind of projection, where three-dimensional reality is encoded on a two-dimensional surface. Another school of thought imagines that black holes connect to other regions of spacetime through wormholes, bridges through which information might leak out in ways we cannot yet detect. In this view, black holes may not destroy information but rather hide it behind layers of geometry that our current theories cannot yet unravel. More recently, theoretical advances in quantum gravity and string theory have offered glimpses of resolution. Some physicists believe that subtle correlations in Hawking radiation could preserve information after all, that the radiation is not truly random, but quantum entangled with the black hole's interior. If that is true, then as the black hole evaporates, its information slowly escapes with it, maintaining the balance demanded by quantum theory. Still, the paradox remains one of the most haunting questions in all of physics. It touches the very fabric of reality, the intersection of the infinitely large and the infinitely small. It asks whether the universe is fundamentally logical and reversible, or if there are places where even logic breaks down. When we gaze into the abyss of a black hole, we are not merely looking at the death of a star. We are confronting the limits of human understanding. The black hole information paradox is a reminder that the universe still guards its deepest secrets, hidden behind the veil of the event horizon, where time, space, and knowledge itself fall into shadow. And yet, somewhere within that darkness, perhaps the answers still exist, preserved, encoded, and waiting to be understood. The Gibbs Paradox. In the late 19th century, when thermodynamics and statistical mechanics were beginning to take shape, scientists were obsessed with one question. What is entropy, really? Entropy, the measure of disorder or the number of possible microscopic configurations of a system, seemed to hold the key to understanding the balance between order and chaos in the universe. It was during these explorations that physicist Josiah Willard Gibbs encountered something deeply troubling, something that didn't make sense, even within the elegant logic of physics. This puzzle would come to be known as the Gibbs Paradox. a quiet but profound contradiction that forced scientists to reconsider what it truly means for particles to be identical. To understand it, imagine a simple thought experiment. You have two identical containers of gas, say, both filled with oxygen. Each container has the same temperature, pressure, and number of particles. Now, remove the wall separating them, allowing the gases to mix. Intuitively, nothing changes. After all, both gases are the same, identical in every way. The pressure and temperature remain the same, and no new energy is released or absorbed. But when Gibbs applied the statistical formulas for entropy to this situation, he found something strange. The entropy increased. According to classical thermodynamics, the mixing of two gases should always increase entropy because it leads to more disorder, more possible configurations of particles. But in this case, there was no real difference between the gases before and after mixing. Nothing meaningful had changed in the physical world, yet the mathematics said entropy had gone up. This was the paradox. If two different gases mix, an entropy increase makes perfect sense. The system becomes more complex and disordered. But if two identical gases mix, there should be no change, since no new arrangements are possible that weren't already allowed before. Gibbs realized that the classical definition of entropy seemed to overcount the possible states of the system, producing a false increase when identical particles were involved. At first glance, this might seem like a small mathematical issue, but it cut to the very core of what matter is. It questioned whether particles are distinguishable or not, whether the universe cares about which atom is which. In classical physics, each particle is unique. Even if two atoms of oxygen appear identical, we can, in principle, imagine labeling them and tracking their individual paths. But in quantum mechanics, something deeper happens. Quantum particles, whether electrons, photons, or atoms, are truly indistinguishable. There is no physical label, no hidden variable, no subtle difference that separates one from another. Exchanging two identical particles doesn't produce a new state. It produces exactly the same state. It was only with the rise of quantum theory in the 20th century that the Gibbs paradox found its resolution. When physicists incorporated the indistinguishability of particles into the equations of statistical mechanics, the artificial increase in entropy vanished. The mathematics began to reflect reality again. This realization led to a deeper understanding of the quantum world. It gave birth to the concepts of Bose-Einstein and Fermi Paradox statistics, the two great families of quantum behavior that describe everything from the light emitted by stars to the structure of matter itself. Bose-Einstein statistics describe particles, like photons, that can occupy the same state without limit, forming strange entities like laser beams and superfluids. Fermi Paradox statistics describe fermions, particles like electrons and protons, that can never share the same state, a rule that explains the structure of the periodic table and the stability of atoms. In essence, the Gibbs paradox was the first crack in the wall separating classical physics from the quantum world. It revealed that our old intuitions about individuality and distinction simply do not apply to the microscopic universe. But even now, the paradox has philosophical weight. It reminds us that identity itself may be an illusion at the most fundamental level. Two particles, separated by distance, time, or even galaxies, may not be two at all, only reflections of the same underlying entity, obeying the same laws in perfect symmetry. The Gibbs paradox also whispers something subtle about the nature of knowledge. Entropy measures uncertainty, and uncertainty depends on what we can or cannot distinguish. When we learn that particles are truly identical, the universe becomes less uncertain, not because it changes, but because we see it more clearly. So, in a sense, the Gibbs paradox wasn't a failure of physics. It was a mirror held up to our own assumptions, showing that what we thought were differences might only be shadows cast by our limited perception. In the end, Gibbs's quiet discovery became a cornerstone of modern physics, bridging the classical and quantum worlds. It is a paradox that did not destroy order but instead revealed the deeper order beneath it, the realization that sometimes, when we stop trying to tell things apart, the universe finally begins to make sense. The Olbers Paradox. Imagine standing beneath a clear night sky, far from cities and their lights. Above you stretch billions upon billions of stars, scattered like glittering dust across an endless black canvas. Feels infinite, eternal, and full of light. Yet, it is also dark. This simple observation lies at the heart of one of the oldest and most haunting questions in science. Why is the night sky dark? It is a question so ordinary that most people never stop to think about it. But when German astronomer Heinrich Wilhelm Olbers asked it in the early 19th century, the answer shook the foundations of how humanity understood the universe. According to the logic of the time, the universe was thought to be infinite, static, and eternal, stretching forever in every direction, filled evenly with stars. If that were true, then no matter where you looked, your line of sight should eventually end at the surface of a star. Just as every direction in a dense forest eventually ends at a tree trunk, every line of sight in an infinite universe should end at a glowing sun. If that were so, the entire sky should blaze with the brightness of the sun. There would be no night, no darkness, only a uniform sea of starlight, as bright as day. But it isn't. The night sky is dark, vast, and quiet. This contradiction between theory and observation became known as Olbers Paradox. Many explanations were proposed in the centuries that followed. Some early thinkers suggested that distant stars might be hidden behind clouds of dust or gas, blocking their light. But this explanation fails upon closer inspection. Over cosmic timescales, such dust would absorb light, heat up, and eventually re-radiate it, glowing just as brightly as the stars it concealed. The darkness would remain unexplained. Others speculated that perhaps the light from distant stars simply hadn't had time to reach us yet. But for that to be true, the universe could not be eternal. It would need to have a finite age. That last idea, dismissed in Olbers' time, turned out to be the key. In the 20th century, with the rise of modern cosmology, scientists began to understand that the universe is not infinite in age, and it is not static. It is expanding, and it had a beginning. According to the Big Bang theory, the universe began around 13.8 billion years ago in a hot, dense state and has been expanding ever since. This means that the light from the most distant stars and galaxies has not yet had time to reach us. The observable universe, the part we can see, is limited by the finite speed of light and the finite age of everything. Furthermore, as the universe expands, the light from distant stars and galaxies is stretched into longer wavelengths through a process called redshift. Light that might have once been visible is now shifted into infrared or even microwave radiation, beyond the range of human sight. In fact, the glow of this ancient light still surrounds us. It is the cosmic microwave background, the faint afterglow of the Big Bang itself, filling the universe in every direction. What we perceive as darkness is not the absence of light, but the fading whisper of light stretched thin by time and distance. The night sky, then, is not dark because the universe is empty. It is dark because the universe is young, dynamic, and expanding. Each point of light we see is not eternal, but a window into the deep past. A message sent billions of years ago from a star that might no longer even exist. Olbers Paradox, in its quiet simplicity, forced scientists to confront the finite nature of reality. It transformed a childlike question into one of the deepest truths about the cosmos. When we look into the darkness between the stars, we are not staring into nothingness. We are looking at the limits of visibility, the boundaries of time itself. The darkness is the silence between the cosmic notes, a pause in the eternal symphony of creation. So, the next time you find yourself beneath the night sky, remember, its darkness is not a void. It is evidence of a universe in motion, still expanding, still cooling, still telling its story. Olbers' Paradox is not a contradiction anymore. It is a doorway to understanding why the universe looks the way it does, and a reminder that even the deepest darkness is filled with ancient light. The Twin Earth Paradox. Imagine a distant planet, orbiting a star far away from our sun. At first glance, it appears to be Earth's perfect twin. The same blue oceans, white clouds, and green continents. The same animals, plants, and even people. A world that mirrors our own so precisely that every molecule seems to have its counterpart. This is Twin Earth, a thought experiment that challenges not physics, but the very meaning of words, knowledge, and understanding. The paradox was introduced by philosopher Hilary Putnam in the 1970s, not as a question about outer space, but as a way to explore the relationship between language and reality. It begins with a simple premise, that somewhere in the universe, there exists another planet just like Earth in every observable way. The only difference lies in one small but crucial detail, the substance that fills its lakes and rivers, that falls from its clouds and quenches the thirst of its inhabitants. On Earth, that substance is H2O, a molecule made of 2 hydrogen atoms and 1 oxygen atom. On twin Earth, the liquid looks, feels, and behaves exactly like water, but it has a completely different chemical composition, something we might call XYZ. To the people living there, this liquid is also called water. They drink it, freeze it, and boil it. They use it to wash their clothes, and they see it falling from the sky. They have the same word for it, the same experiences, and the same scientific culture. From their point of view, nothing is different. Now, imagine 2 identical individuals. One on Earth, one on twin Earth. Both point to the clear liquid around them and say, "This is water." On the surface, their statements seem identical. But according to Putnam, they are not saying the same thing. This is where the twin Earth paradox emerges. The paradox asks, if both people use the same word, water, and even share the same internal understanding of it, how can they be referring to 2 different substances? How can meaning depend on something beyond what is in the mind? Putnam's answer was revolutionary. He argued that the meaning of a word is not determined solely by what's inside our heads, but also by our connection to the external world. In other words, words gain meaning not only through thought or definition but through causal relationships with the things they describe. The word water refers to H2O on Earth because of our world's physical chemistry, not because of how we think about it. On twin Earth, the word water refers to XYZ, not H2O, even though both groups of people have identical mental states. Thus, meaning depends on environment and context. Our thoughts, no matter how precise, are inseparable from the physical world in which they exist. This realization reshaped the philosophy of language and mind. It suggested that human understanding is always partially external, that reality itself participates in the act of meaning. Even if we were perfect copies of ourselves on twin Earth, our words, beliefs, and knowledge would subtly differ because the world they describe is different. Beyond philosophy, the twin Earth paradox resonates deeply with science. It reminds us that our observations are tied to the structure of the universe itself. A concept that seems universal might not be, once the underlying reality changes. And perhaps there's something poetic about that. The paradox suggests that meaning is a bridge between mind and matter, between thought and the universe it tries to describe. It shows that even our most familiar words, like water, contain an invisible link to the world beyond us. In a broader sense, twin Earth reflects our search for identity in a vast cosmos. What defines us? Our DNA, our thoughts, our chemistry, or the world we inhabit? If there are beings who think and feel just as we do, but live in a universe built on slightly different laws, are they still us? When we look up at the stars, wondering if there's another planet like ours, the twin Earth paradox reminds us that even perfect reflection hides a difference too deep for the eye to see. And it leaves us with a quiet, almost meditative truth, that understanding the world is not only about what we know, but also about where, and in what universe we stand. The arrow of time paradox. Every moment of your life moves in one direction, forward. You wake, you age, and you remember the past but not the future. A glass may fall and shatter into pieces, but those pieces never leap back together. Smoke disperses into the air, but it never gathers itself again. Time, it seems, has a direction, a one-way flow from past to future. But when we turn to the fundamental laws of physics, something strange happens. Those laws, whether in classical mechanics, relativity, or quantum theory, do not actually prefer one direction of time over the other. They are time-symmetric. If you were to reverse every motion in the universe, every orbit, every collision, every vibration, the equations would still work perfectly. The universe, at least mathematically, doesn't care which way time runs. And yet, we do. This contradiction between the symmetry of physical laws and the unmistakable direction of time in our experience is known as the arrow of time paradox. The first person to formally describe this arrow was physicist Arthur Eddington in the 1920s. He observed that, although the equations of motion allow both forward and backward progression, the world we inhabit seems to have a clear temporal bias. The question, then, is simple yet profound: why? Why does time have an arrow when physics says it doesn't need one? To find the answer, scientists look to the second law of thermodynamics, the law of entropy. It states that in any closed system, entropy or disorder always increases over time. In other words, systems evolve from order to chaos, from structure to randomness. Ice melts, energy disperses, and stars burn out. This tendency gives rise to the flow of time we perceive. The universe moves toward higher entropy, and that movement defines the forward direction. The past is the realm of low entropy, of order, simplicity, and coherence. The future is where disorder grows. The arrow of time, then, is not built into the laws of motion, but into the initial conditions of the universe itself. And this is where the paradox deepens. If the universe is governed by reversible laws, why did it begin in such an improbably low entropy state? Why did the Big Bang, an explosion of unimaginable energy, start with such extraordinary order? It is this mystery that anchors the arrow of time paradox. The question is not why entropy increases, it's why it had room to increase in the first place. Some physicists have proposed that the answer lies in the geometry of spacetime. As the universe expands, the fabric of space stretches, creating more possible configurations for matter and energy to occupy. Entropy rises naturally as a result. In this sense, the arrow of time might be tied to the cosmic expansion itself. Others have looked to the possibility of multiple universes or cyclical cosmologies, where each universe begins with a fresh arrow of time, pointing away from a shared moment of low entropy. In such models, time could flow in opposite directions on opposite sides of a cosmic boundary, our future being someone else's past. But perhaps the most haunting aspect of the paradox is its connection to human experience. We don't just see time's arrow, we feel it. Memory, decay, cause and effect, all these phenomena depend on entropy. We remember the past because information about it has been physically recorded in the structure of the world, in neural patterns, fossils, photons, and data. The future, by contrast, is unrecorded, undefined, still waiting to happen. In a world where all physical processes could, in principle, run backward, our psychological experience anchors us in one direction. We move forward not because physics demands it, but because reality unfolds in increasing disorder, and consciousness follows that gradient. Some physicists believe that one day, if the universe stops expanding and begins to contract, entropy might decrease, and time could reverse. Others argue that such reversal would be indistinguishable from annihilation itself. Everything that defines forward would simply cease to make sense. For now, the arrow of time paradox remains one of science's most beautiful mysteries. It is a reminder that the universe is both reversible and irreversible, symmetrical and yet irrevocably tilted toward the future. Every breath, every falling leaf, every fleeting second is a reflection of that hidden imbalance. The arrow of time, invisible yet absolute, is what gives the universe its story, one that can only be read from beginning to end. And perhaps, somewhere beyond our perception, beyond the cosmic horizon, there exists another arrow pointing the other way, a mirror universe where what we call the past is still yet to come. The EPR Paradox. In 1935, three of the greatest scientific minds of the 20th century, Albert Einstein, Boris Podolsky, and Nathan Rosen, set out to challenge what they saw as an unsettling feature of quantum mechanics. They published a paper that would become one of the most famous in the history of physics, describing what is now known as the EPR paradox, a thought experiment so strange that it still shapes the debate over the nature of reality itself. At the heart of the paradox lies a simple but troubling question. Can two particles be connected in such a way that measuring one instantly affects the other, even if they are separated by vast distances? Quantum mechanics, according to its mathematical framework, seem to say yes. When two particles interact, they can become entangled, meaning their properties become linked in a way that defies classical explanation. Measure the spin, position, or momentum of one particle, and the other will instantly take on a corresponding value, no matter how far apart they are. Einstein found this deeply disturbing. He famously called it spooky action at a distance, believing it violated one of the most fundamental principles of physics, that nothing, not even information, can travel faster than the speed of light. In the EPR paper, Einstein, Podolsky, and Rosen tried to expose what they believed was an incompleteness in quantum theory. They imagined two particles that interact and then move far apart. According to quantum mechanics, before measurement, both particles exist in a superposition, a cloud of possible states. But the moment one particle is measured, its wave function collapses into a definite state, and the other particle's state becomes instantly determined. To Einstein, this implied one of two possibilities. Either information travels instantaneously across space, which would break the laws of relativity, or quantum mechanics is missing something fundamental, some hidden variables that determine outcomes behind the scenes. He favored the second option. He believed that quantum mechanics was not wrong but incomplete. There had to be some deeper layer of reality governing these correlations, something local, causal, and sensible. But the decades that followed would bring results Einstein never expected. In the 1960s, physicist John Bell proposed a way to test whether such hidden variables could exist. He derived what became known as Bell's inequalities, a set of mathematical limits describing the kinds of correlations possible in any local, realistic theory. If quantum mechanics violated these inequalities, it would mean that the universe does not behave according to classical notions of locality and realism. Experiments began in the 1970s and have continued ever since with increasing precision. Again and again, the results have confirmed that Bell's inequalities are indeed violated. Entangled particles behave as quantum mechanics predicts. Their correlations cannot be explained by any local hidden variable theory. This means that, on some level, nature really does exhibit non-local connections, instantaneous correlations that transcend space. The outcome of one measurement seems to influence another across light-years of distance, even though no signal passes between them in the classical sense. However, this does not mean faster-than-light communication is possible. The influence is not a signal. It carries no usable information and cannot be controlled. It simply reflects the deep, holistic structure of quantum reality. The EPR paradox, then, reveals something extraordinary: that the universe may be fundamentally interconnected in ways that classical intuition cannot capture. Entangled particles are not two separate things influencing each other across space. They are one system, described by a single quantum state, no matter how far apart their parts may be. This realization gave rise to the field of quantum information theory and inspired technologies like quantum cryptography and quantum computing. It also continues to challenge our understanding of what separation and distance even mean. Einstein never accepted this vision of reality. He died believing that there must still be a more complete, deterministic theory hidden beneath the probabilistic surface of quantum mechanics. Yet, ironically, the very paradox he helped formulate became the cornerstone of the quantum revolution, a gateway to understanding that the universe, at its deepest level, may be non-local, entangled, and inseparable. The EPR paradox stands as both a scientific and philosophical mystery, a reminder that reality is not what it seems. The boundaries we imagine between here and there, between one thing and another, may only be illusions cast by a deeper unity, one that ties every particle, every star, and every moment together in an invisible quantum web. The Monty Paradox. At first glance, it seems like a simple game, a harmless puzzle of chance. Yet hidden beneath its playful surface lies one of the most unintuitive mathematical paradoxes ever conceived. The Monty Paradox, named after the host of the 1960s television show Let's Make a Deal, has confounded mathematicians, scientists, and ordinary people alike. It's a riddle that shows just how far our human intuition can drift from the cold precision of probability. Imagine this: you're standing on a game show stage. In front of you are 3 closed doors. Behind one of them is a gleaming new car. Behind the other 2, goats. You pick one door, say door number 1. The host, Monty Hall, who knows what's behind each door, doesn't open the door you chose. Instead, he opens one of the remaining 2 doors, say door number 3, and reveals a goat. Then he turns to you with a smile and asks, "Do you want to stick with your choice, or switch to the other unopened door?" Most people, guided by intuition, assume it doesn't matter. There are 2 doors left, so surely there's a 50-50 chance now, right? But the math says otherwise. The truth defies our instincts. The correct choice, the one that doubles your chances of winning, is to switch. Here's why. When you first chose door number 1, your chance of picking the car was 1 in 3. That means there was a 2 in 3 chance that the car was behind one of the other 2 doors. When Monty opens a door to reveal a goat, he isn't doing so at random. He's giving you information. He always opens a door with a goat, which effectively transfers the entire 2/3 probability to the door that remains closed. By switching, you're not just guessing again, you're leveraging that new information. Statistically, your odds jump from 33% to 66%. It sounds simple in hindsight, but when this paradox was first popularized, it caused an uproar. In 1990, the puzzle appeared in Parade magazine, posed by columnist Marilyn Vos Savant, who held the record for the world's highest IQ. When she wrote that the best strategy was to switch doors, she received thousands of letters, many from mathematicians and scientists, insisting she was wrong. Even professionals who worked with statistics daily found the result emotionally unacceptable. People are wired to believe that once one option is eliminated, the remaining 2 must be equally likely. Yet this is a perfect demonstration of how human reasoning often fails when confronted with probability. To make it clearer, imagine an exaggerated version of the same game with 100 doors instead of 3. Behind one door is a car. Behind the other 99, goats. You pick one door. Your odds of being right are 1 in 100. Then the host, knowing where the car is, opens 98 doors, all showing goats, leaving only your original door and one other closed door. Would you still stick with your first choice? Probably not, because the odds that the car is behind your door are still 1 in 100, while the odds that it's behind the other unopened door are 99 in 100. In this extreme version, switching feels obvious. Yet, in the 3-door version, the same principle applies, it's just less visible to intuition. The Monty Paradox teaches a humbling lesson about perception and probability. It reminds us that our minds are not naturally built for statistical reasoning. We're creatures of pattern and emotion, not pure logic. We see fairness and symmetry even where none exist. This paradox also reveals how easily we underestimate the power of information. The host's knowledge of what lies behind the doors changes the structure of the problem entirely. Once Monty opens a goat door, he's not merely reducing the number of options. He's reshaping the probability landscape. In a way, the Monty problem is a metaphor for life itself. We make decisions based on incomplete information, often clinging to our first choice because it feels like a commitment. We grow attached to our initial paths, even when the universe subtly reveals a better option. Switching requires humility, the willingness to admit that the odds may not be in our favor, and that new information can and should change our minds. It's a mathematical puzzle, yes, but also a psychological mirror, a reflection of how we deal with uncertainty, belief, and change. The next time life presents you with 3 doors, 1 promising, 2 deceptive, and a moment comes when new evidence opens one of them, revealing what lies behind. Remember the Monty Paradox. Sometimes the wisest move is to switch. The twin photon paradox. Among the most curious and subtle paradoxes in modern physics lies the twin photon paradox, a thought experiment that stretches the limits of Einstein's theory of relativity and challenges our understanding of simultaneity, time, and motion at the speed of light. To begin, imagine 2 photons, 2 identical particles of light, emitted from a single event. They are born together, perhaps from the same atom, and then sent in opposite directions through the vast emptiness of space. Both travel at the speed of light, the ultimate cosmic limit, carrying energy but no mass, with no sense of rest or duration in the traditional human meaning of time. Here's where the paradox begins to unfold. From our perspective, an observer at rest, both photons move away at light speed, each covering unimaginable distances as time flows forward. But if we could somehow imagine the world from the photon's point of view, things would look profoundly different. According to Einstein's special relativity, as an object approaches the speed of light, time slows down and distances contract. At the exact speed of light, time would effectively stop and space itself would shrink to nothing. That means, for a photon, the entire journey from its emission to its absorption would happen instantaneously. To the photon, there is no sense of travel, no before or after, no distance to cross. It simply exists at the point of emission and absorption simultaneously. Now return to our two photons, the twins, born together, heading in opposite directions. From our external viewpoint, they move farther and farther apart, perhaps billions of light-years away. Yet from their own hypothetical frame of reference, if such a frame could exist, they never separate at all. That's the essence of the paradox. How can two photons be infinitely distant from each other in one frame of reference, yet occupy the same point in another? The laws of physics tell us that photons have no rest frame. You cannot ride along with a photon, because doing so would require infinite energy and break the structure of relativity itself. Still, thinking about what the world would look like if you could forces us to confront the strange, counterintuitive geometry of spacetime. This paradox echoes the famous twin paradox, where one twin travels near the speed of light and returns younger than their sibling who stayed behind. But in the photon version, the situation reaches its extreme. For a massive traveler, time only slows. For a photon, it stops completely. There is no aging, no motion through time, only existence in an eternal now. From our human perspective, this creates a deep tension in how we imagine causality and separation. If the two photons never experience time or distance, then in a very real sense, they remain connected. Their shared origin defines them forever. This strange timelessness isn't just theoretical, it underlies much of quantum physics. In quantum entanglement, two particles can remain correlated across vast distances, influencing each other instantaneously in ways that seem to defy relativity. The twin photon paradox feels like a geometric reflection of that mystery. A spacetime paradox, where light itself refuses to obey our linear sense of time. Some physicists interpret this through the structure of spacetime itself. In the four-dimensional universe described by Einstein, light doesn't move through time as we do. It traces the light cone, a boundary between what can and cannot be causally connected. Every photon, therefore, lives on the edge of causality, connecting events that for us are separated by vast distances and ages. To the photon, though, all of that collapses into unity. The beginning and the end of its journey are not two moments. It experiences them as one. And so, the twin photon paradox is less about contradiction than revelation. It reminds us that reality changes depending on how fast you move through it, that time is not universal, and that simultaneity, the idea that two events can happen at the same time, is only an illusion of perspective. For humans, anchored in slow-moving matter, time feels like an unbroken river. But for light, it is a frozen lake. Still, eternal. When we gaze into the night sky and see photons that left distant stars billions of years ago, we're not just seeing the past, we're touching something timeless. For those photons, their birth and their arrival in your eyes are one and the same event. In that quiet realization, the paradox resolves into something almost poetic. The universe is not just a sequence of moments, but a single, connected whole. And light, traveling endlessly between stars, is the thread that binds it all together. The Maxwell's demon. In 1867, the Scottish physicist James Clerk Maxwell imagined a tiny, invisible creature that could break one of the most fundamental laws of physics. This creature would later become known as Maxwell's demon, and its existence, if only as a thought experiment, would haunt scientists for over a century, challenging our understanding of entropy, information, and the very nature of order and disorder in the universe. To understand the paradox, we must begin with the second law of thermodynamics, the law that says entropy or disorder in an isolated system can never decrease. It's the principle that explains why hot coffee cools down, why buildings crumble over time, and why the universe itself drifts slowly toward chaos. Entropy is time's arrow, pointing from order to disorder, from energy to equilibrium. But Maxwell's demon dared to ask, what if something could cheat this law? Imagine a closed box divided into two chambers by a wall, with a small door between them. Inside the box, millions of gas molecules bounce randomly around, colliding and spreading energy evenly. Some fast, some slow, but on average balanced. According to thermodynamics, This system should stay at the same temperature forever, unless energy is added or removed from the outside. Now picture a tiny being, a demon, guarding the door. It's not malicious. It's more like an infinitely clever gatekeeper. It watches the motion of every molecule, opening and closing the door with perfect timing. Whenever a fast, hot molecule approaches from the left, the demon lets it pass to the right side. Whenever a slow, cool molecule moves toward the left, it opens the door for that one instead. Over time, the right side fills with fast, energetic molecules, becoming hotter, while the left side fills with slower ones, becoming colder. The demon has created a temperature difference, seemingly out of nothing, without doing any measurable work. But that's impossible, or at least it should be. The second law of thermodynamics forbids such a process. It says that in a closed system, heat cannot spontaneously flow from a cold region to a hot one. And yet, the demon appears to make it happen simply by sorting molecules intelligently. If such a being could exist, it would be able to power an engine indefinitely, generating energy from pure information. It would mean that knowledge itself, observation, could substitute for physical energy. This was the heart of the paradox. Could information reduce entropy? Could knowing something about a system allow one to manipulate it in ways that break physical laws? For decades, physicists wrestled with the idea. Some argued that the demon's act of measurement must somehow require energy. Others claimed that the paradox exposed something missing in our understanding of thermodynamics itself. It wasn't until the mid-20th century that a solution began to emerge. Scientists like Leo Szilard and later Rolf Landauer realized that the demon's real limitation lay not in opening doors or watching molecules, but in memory. Each time the demon observes a particle, it must record what it sees, fast or slow, left or right. Eventually, its memory fills up. To continue functioning, it must erase old information. And according to Landauer's principle, erasing information is a physical act. It produces heat, increasing entropy. In other words, the demon cannot outsmart the universe. The energy cost of processing and forgetting information perfectly balances the entropy it tries to remove. The law of thermodynamics survives intact, but with a deeper understanding, information itself has physical consequences. The resolution of Maxwell's demon revealed something profound about the connection between knowledge and energy. It showed that information is not abstract. Every bit stored, processed, or deleted corresponds to real physical change. This insight quietly transformed modern science. It gave birth to information theory, influenced quantum mechanics, and shaped the foundations of computing and artificial intelligence. In a strange way, Maxwell's imaginary creature predicted the digital age, a world where information, like energy, drives the evolution of systems both natural and artificial. But even as the paradox was resolved mathematically, its philosophical echoes remain. The demon reminds us of how fragile our intuitions are when confronted with the deep logic of the cosmos. It blurs the boundary between observer and participant, between thought and matter. Every time you delete a file, your computer produces a trace amount of heat, an echo of Maxwell's demon. Each decision, each observation, each act of distinguishing order from chaos has a physical cost. The paradox, then, is not merely about a mischievous creature defying physics. It's about the universe's hidden accounting system, where even the act of knowing changes the state of reality. And so, the demon lingers, not in laboratories or boxes, but in every bit of data, every algorithm, and every thought that rearranges the order of things, whispering a quiet truth about existence. That information, like energy, can never be free. The Ship of Theseus. Among the oldest and most haunting paradoxes in philosophy and science alike is the Ship of Theseus, a puzzle that questions the very meaning of identity, persistence, and change. It asks a deceptively simple question. If an object has every one of its parts replaced over time, does it remain the same object? The story begins in ancient Greece, with the legendary hero Theseus, who sailed to Crete to slay the Minotaur and returned to Athens as a symbol of triumph and renewal. To honor his memory, the Athenians preserved his ship in the harbor for centuries. But as time passed, the wooden planks began to rot. The caretakers replaced each piece gradually, one board after another, then the masts, the sails, the oars, until not a single original part remained. And then came the paradox. Was the restored vessel still the Ship of Theseus, or had it become something entirely new? At first glance, the answer seems obvious. Of course, it's still the same ship. One might say it was repaired, not rebuilt. After all, identity, in a practical sense, is tied to continuity. The ship never ceased to exist. It was maintained. Yet when reason pushes deeper, the certainty begins to dissolve. If the identity of an object lies in its material components, then once every plank has been replaced, the ship is no longer the same. It merely looks like it. But if identity lies in form, function, or history, then perhaps it is the same ship, because its shape, purpose, and story endure, even as its parts change. Philosophers have argued both sides for centuries. The Greek historian Plutarch first recorded the paradox, and later, Thomas Hobbes expanded it with an unsettling twist. Suppose that while the Athenians were replacing the ship's parts, someone collected the discarded planks, restored them, and rebuilt the original vessel elsewhere. Now we have two ships, one made of the original materials, the other preserved by continuous maintenance. Which one is the real Ship of Theseus? There is no definitive answer. The paradox exposes a tension between two ways of defining identity, continuity and composition. It challenges the notion that something must remain physically the same to remain itself. Over time, this ancient thought experiment evolved far beyond ships and wood. It became a metaphor for the human condition. Our bodies, too, are in constant change. Every few years, nearly every cell in the human body is replaced. Our thoughts shift, our memories fade, our identities evolve. Yet we still say, I am the same person I was years ago. Are we? Or are we, like Theseus's ship, mere vessels of continuity, carrying forward only the illusion of sameness? Modern science deepens this paradox even further. In neuroscience, the structure of the brain continually rewires itself, forming new connections while pruning old ones. The self, it turns out, may not be a fixed entity at all, but a dynamic process, one that changes from moment to moment, yet feels unbroken. In quantum physics, similar questions arise about the identity of particles that appear identical but cannot be distinguished from one another. And in artificial intelligence, the paradox takes a futuristic form. If we could perfectly replicate a person's consciousness in a machine, would that copy be the same individual or merely a reflection? The Ship of Theseus thus becomes more than a philosophical puzzle. It is a mirror held up to reality itself. It asks not just what things are, but what it means for anything to persist through time. Perhaps the paradox teaches that identity is not a matter of material permanence, but of narrative continuity. What makes something or someone the same is the story that connects its moments, the unbroken thread of experience and recognition. The ship remains Theseus's not because its wood endures, but because its journey does. In this sense, every being and every object is a ship of Theseus. We are all composites of renewal, ever-changing yet tethered to our own pasts. What we call self may be nothing more than the memory of movement, the persistence of pattern amidst transformation. And so, the paradox endures because it reflects a universal truth. Everything changes, and yet somehow, everything remains. When you look at an old photograph of yourself and whisper, "That's me," you are invoking the same mystery the Athenians once saw in their harbor. A mystery that stretches across time, between identity and impermanence, between what was and what still is. The ship of Theseus sails still, not on the seas of Greece, but through every life that wonders what it truly means to stay the same while endlessly becoming something new. Ending. And so, our quiet journey through the greatest paradoxes in science comes to an end. From time and relativity to light, entropy, and identity, each mystery reminds us how little we truly know, and how beautiful that unknowing can be. The deeper we look into reality, the more it bends, revealing that the universe itself is a paradox, full of wonder and contradiction. If you enjoyed this calm exploration of the unknown, I'd be truly grateful if you left a like to support the channel. Don't forget to subscribe, so you won't miss the next journey through science and mystery. Share your thoughts below, Tell me which paradox made you think the most, or which one you'd like to hear more about next time. And if you know someone who would enjoy this quiet voyage through logic and imagination, feel free to share this video with them. Thank you for watching, for thinking deeply, and for spending this time with me. Until next time, take care, rest well, and may your night be filled with calm and sweet dreams.